Okay, for our final lesson in the unit, we are combining a quick congruence shortcut that is useful in right triangles, and then a way to think about using CPCTC or noticing if we have parts of triangles that are overlapping each other using the reflexive property of congruence to show congruence in that particular situation. So our job again is to make sure that we're able to identify congruent right triangles, and we'll start with lesson 5 first. So we know what a right triangle is. This is review, but a right triangle is a triangle with a right angle. And we know that this is a right angle because we have the sides marked perpendicular, and by the definition of perpendicular, this is a right angle. The hypotenuse is the longest side of the right triangle. It's the side that is opposite from, if you were to draw an arrow through this vertex to the opposite side, it would point to the hypotenuse. The other sides of the right triangle are referred to as the legs of the right triangle. So that's hopefully not new information, but if not, wanted to make sure that I was clear on that. Write it down regardless, have those 3 vocabulary terms handy. And what we're going to learn is that if we have a pair of right triangles and their hypotenuses are congruent and one pair of legs are congruent, then that means that the triangles must be congruent. So in the past, we've been told, and we've been quite explicit, that angle side side, wink wink, we're not allowed to use angle side side as a shortcut for triangle congruence, but it does work with right triangles. And so the question here is why? Basically, the rule here is that if a squared plus b squared equals c squared, then c squared minus b squared would equal the same amount, a squared. And so this would kind of revert back to a side-side-side congruence. And so if we can show that that's true in right triangles, then we can apply this concept knowing basically the same, or not the same, but knowing 3 pieces of information, a right triangle with 2 pairs of congruent sides, this works. We call this the hypotenuse leg theorem. If the hypotenuse and a pair of, the hypotenuses and a pair of legs in a right triangle or a pair of right triangles are congruent, then that means that the triangles are congruent. So, given that segment AD is a perpendicular bisector of segment CE, and knowing that CD is congruent to EA, prove that these triangles are congruent. So the way that we're going to approach this is, since AD is the perpendicular bisector of CE, it means that it is making right angles at B, and it is cutting segment CE into congruent parts. And then of course we have the hypotenuses given as congruent also. So based on this information, we mark the diagram accordingly. We know that this is given to us, and so we know by the definition of perpendicular that the angles formed around B are going to be right angles. So this is a right angle here, and this is a right angle there, because of what perpendicular means, which means that these triangles are right triangles. All right, we have to have right triangles so that we can use the hypotenuse leg theorem. We're then going to say that the hypotenuses are congruent, that's given, and we know by the definition of bisect that these parts of segment CE are also congruent to each other. So we have a pair of hypotenuses, a pair of legs, therefore the triangles are congruent by the HL theorem. All right, so the thing that is kind of different about this proof, it's going to be 6 steps, right, is we have to have perpendicular so that we can have right angles, and then that means that we have right triangles. All right, those statements are going to be the same 3 statements in all of our hypotenuse leg proofs, unless we're told that they are right triangles from the get-go, or if we're told that we have right angles from the get-go. But usually we're going to be given that we have perpendicular segments, which means that we have right angles, which means that we have right triangles. So be prepared to write those 3 statements down so that we can use hypotenuse leg and our hypotenuse leg theorem. That's basically it for lesson 5. All right, but for lesson 6, where we kind of move on to understand triangle congruence and overlapping triangles, we're going to be a little more keen on our visual thinking. We have to think about what we're seeing and maybe separate out our triangles so that we can write out our triangle congruence statement. So here we have what looks like a quadrilateral, right? 1, 2, 3, 4. But really what this is a pair of overlapping triangles. And so we can see here that we are able to separate those triangles apart but there is always a common or shared reflexive either angle or side. A lot of times the reflexive side is really easy to see, and we use that so much that sometimes it's not as obvious to recognize the congruent or shared angle. All right, so we're going to separate it out and look for overlapping shared congruent parts. So here in this triangle, we are going to, it says you do. This is a little harsh, so I'm not going to have you do it. I'm actually going to work it out for you. We're going to have that this triangle right here, which is ZWX, and then I'm going to draw the other overlapped triangle over here, YXW. We can tell that we are given ZXW is congruent to YWX. We are also told that ZWX is congruent to YXW. And we're supposed to somehow prove that ZW, this segment, is congruent to that segment, YX. So this is kind of an interesting proof. I don't know why it says you do. There's no way that you're doing this. And so, or maybe you are. Surprise me. Let's pause the video and see what you do. Now, I can tell that there is this overlapping part. Side WX is the same as segment XW. They're just in different triangles. We're going to read them different ways. WX is congruent to XW by the reflexive property of congruence. So what I want for you to do is show that these two triangles are congruent using angle side angle. And then what I want for you to do, is say that these pieces are congruent by CPCTC, or the definition of congruent triangles. So go ahead, and I've mapped it out for you. I've drawn those, I've labeled them. What I want you to do is say that we have pair of angles congruent, pair of reflexive sides congruent, pair of angles given congruent. So we have triangles congruent by angle side angle, and therefore these sides are congruent by CPCTC, or the definition of congruent triangles. I'd love to see you write out that proof. All right, so that's, I guess, why it says you do. So we're going to use that to try to do this proof, which is a little more challenging. So pause the video. Hopefully you went ahead and did that proof. That'd be awesome if you did. Over here, we are going to prove that triangle QPT is congruent to triangle QRT. And the way that we're going to do that is we are going to prove a different pair of triangles congruent and then use the definition of congruent triangles. We've got some overlapping awesomeness happening here. So what I'm going to do first is I'm going to show that this big triangle, QPS, is congruent to this big triangle, QRS. Now I know I'm already marked and given that these sides and angles are congruent. And then by the reflexive property of congruence, I know that QS is congruent to itself. So here's what that's going to look like. PS is congruent to RS given. Angle PST, or PSQ we could call it, is congruent to RST, or RSQ. And SQ is congruent to itself. All right, this big segment right here. Since we have side angle side triangles congruent, I know that PSQ and RSQ are congruent to each other. All right, now that that's done, now I can get a little creative because I want to show that these two triangles are congruent. And there's a couple ways in which we can think through that. Looking at this triangle, this little triangle right here, it has this same segment, QP and QP. Well, we know that QP is congruent to QR from CPCTC over here. And I know that the angles at Q are congruent to each other. I'll mark those twice by CPCTC. And then I know that this segment QT is going to be congruent to itself by the reflexive property of congruence. And therefore, these two triangles are congruent using side angle side. So I'm going to say that PQ and RQ are congruent because that was from the definition of congruent triangles. If you don't like CPCTC, again, just a reminder, we've been writing definition of congruent triangles in class. We've also been writing CPCTC, but whatever floats your boat. Angle PQT at the top is congruent to angle RQT by the definition of congruent triangles. All right, I know that these triangles overlap, so it's kind of maybe hard to see, if that's point T, that we have CPCTC from another pair of triangles. We also have QT congruent to itself by the reflexive property of congruence, and therefore those triangles QPT and QRT are congruent by side, angle, side. All right, hopefully, this is a pretty challenging proof. I'd love to see if you have any questions or concerns on that. That, folks, is the end of this pretty short lesson, because we've kind of gotten a lot of the hard work out of the way with the side angle side, the angle side angle, the side side side, the angle angle side, and then we get to use those along with the definition of congruent triangles to kind of address other situations. And hopefully hypotenuse leg went well for us. Those are going to be a little clumsy as far as those proofs go, because they're going to require us to write, oh, we've got perpendicular segments, we've got right angles, oh, those are right triangles. So now I can use hypotenuse and leg to show that those triangles are congruent. Please see me with questions.